Okay, so welcome to today's webinar on Nastran In-CAD, titled Connecting Parts and Assemblies. My name is Matthew McKnight. I'm a technical specialist with Autodesk, looking after a range of products, including one of which is the Nastran In-CAD product. This webinar is following on from a number of other webinars that we've conducted over the last couple of weeks. The third in the series, we've already run through what is In-CAD and how to know if you have a good mesh in In-CAD. And next week we'll be running through working with contact constraints in In-CAD as well. So good value in a lot of these webinars, so please keep these in mind and make sure that you can attend if you've got some time spare. Otherwise, we'll get stuck into today's webinar, and if we just look at the agenda, so firstly we'll talk briefly for a few moments on why we use FEA or simulation. Then we'll look at how to connect parts and assemblies inside the environment. We'll look at connectors and contacts separately and together, and we'll work through some examples and then go on and answer some questions and point you in the direction of where you can find some more information associated with the Nastran product. Okay, but so first, why do we use FEA, or more particularly, why do we use simulation? Well, more than likely it's because you're trying to solve a problem that you can't quite understand. So you might be solving an issue with the design, or you might be looking at a new design that you've not created before and just trying to understand the physical behaviors of those components or parts that you're looking at designing. You might even be looking at parts that have failed in the field, and then you're trying to understand why they may have failed and how you can resolve or ensure that they're not failing thereafter. So this is where simulation comes into play, is that it gives you the ability to be able to analyze your designs and look at the way that they're going to react under real-world situations long before you've made any parts. If we break it down and look at it in a graph form as part of the design life cycle, we talk about simulating early and often, and the reason is that whilst an idea is being formulated, so your ability to be able to affect change to your design, it's very easy during the conceptualization stage. So if you consider an idea that's in your head or is just an idea that's sketched on a napkin, then it's very quick and easy to make changes. But the closer you get to releasing that product to production, the harder it becomes to influence change on that part. Inversely associated with that, then you've got the cost of design change. And cost of design change at the conceptualization stage, so whilst it's just an idea or it's a sketch, is relatively quick and easy with very little cost. But then the cost associated with making change further down the track, leading into production, becomes more and more prohibitive. So if we look at a typical cost process curve, you can see here that the cost is predominantly incurred during the testing stage, and then after testing leading through to manufacturing and field, we actually get a reduction in cost. But there's a lot of benefit in actually shifting that simulation stage, where you'd be doing physical testing much earlier into your design process, back towards the conceptualization and early design and engineering stages. And as a result, you'll actually find that you'll get a reduction in cost associated with implementing simulation earlier. So what does this really result in? It results in a number of things, predominantly better quality parts. So if you know how your parts are going to react and you're designing that into your parts earlier, then you're better assured of having better quality designs. Cost, you're reducing your costs because you're not finding out at the last moment that there's issues associated with your parts, and they're not going to perform as you would expect them to. So there's not as much design change. So there's a cost benefit associated with that, and likewise with time. If you're simulating often and early in your design process, there's more likely that you're actually going to save time as a result of that, because you don't have delays later in the program when you're trying to correct issues that have resulted through unknown variables. So let's move on to the core of today's webinar, and that is how to connect parts and assemblies inside Nastran In-CAD. And in doing this, we're breaking it down into two areas. There's really connectors and there's contacts. So let's have a look at connectors first. And there's a number of ways that we can define connectors, and really what we're doing here is we're trying to simplify the use of, simplify our analysis by reducing unnecessary geometry that needs to be defined in the context of an assembly. So in this case, we can simplify our geometry by representing certain entities in our design through connectors. In this case, our first connector is a rod connector. And rod connectors can be defined using some very basic information. So realistically, all you need is cross-sectional area of the rod, polar moment inertia, which you may not necessarily need, the stress recovery location, again, which you don't necessarily need. And these rod connectors enable you to run analysis on, a representation of a rod under both tensile and compressive loads, but not bending. So that's one thing to keep in mind. So you can't actually capture bending as a part of this process. Realistically, all that you need to be able to define a rod location is 2 sketch points. So you define the start of the rod and the end of the rod, and it defines the rod as a straight line connection between those 2 points. And we'll work through an example of that a little bit later. Cable as another type of connector that can be defined, and this is rather unique to Nastran In-CAD. So our other simulation tools don't necessarily have the capabilities to be able to define and work with cables, definitely not in the simplified format that we can inside the Nastran In-CAD product. So the way that we can do it is very similar to rods actually, and so we define some parameters associated with the cable. In this case, any cable slack that might be in the cable, any tension that's on the cable, allowable stresses. We can have the cross-sectional area, the moment of inertia as well. But we need to realize that cables are a tension-only connector. So they will take tension, but they will not take compression for obvious reasons. Like we've shown, with this allowance for preload and slack. And again, like the rods, all we need to be able to define a cable is 2 sketch points. So we just need to have an endpoint for each end of the connector to be able to define a cable. Springs are another way that can be something else that can be defined. We won't be covering springs today, but understand that they can be used using directional stiffness or a damping value, which can be restrictive on any degree of freedom. Again, all that you need is 2 sketch points or vertices to be able to define the location of the springs. And a rather unique way of using springs is to help you stabilize models. So if you've got models that aren't stabilized, they don't have, you're not restricting sufficient degrees of freedom for one reason or another, you can define weak springs to help you stabilize the model and restrict the movement of components. Another connector, and this is one that's used more commonly, is a rigid body connectors, and there's 2 forms of using the rigid body connector. There's one using the rigid, which we'll talk about here. This is what's referred to as RBE2 in Nastran. It's fully rigid, but as a result of that, it adds stiffness to the model, and you need to take that into account when working with this type of connector. It works with an independent sketch point, so it's a sketch point that's not defined in the context of, it's not defined as a feature of the 3D geometry that you're working with predominantly, and you define it in the context of a dependent, which would be the face or edge or 3D or a sketch point, and that would link that rigid those elements back to those points and the faces and geometry that you're selecting. Alternatively, there's the rigid body interpolation, and the difference here is, apart from a naming convention inside the Nastran solver, so this is referred to as RBE3 rather than RBE2, but it uses a method of averaging the nodes of the associated geometry, and the result of this is that it doesn't add the stiffness to the model that we see as a result of the rigid option being selected under the rigid body type. Again, all that's required in this case is the reference point, so a sketch point or vertex, and then some entities that you'd like to associate the connection to. So in this case, it could be faces, edges, or a sketch point as well. And then probably one of the more common forms of connectors that you would use is a bolted connector. You can see a typical example here. So the blue and red are representations of the bolt, the nut, and the washers. So they're just a visual representation to show you where the bolt is. It doesn't actually model in the geometry associated with this. And we can define bolted connections in a number of ways. We can have bolts and cap screws, which we'll talk about and show a little later. And there's a number of parameters that are associated with them. So in doing so, when you set up a bolted connection joint, then in essence you're adding beam and bar elements that define the bolt in context to the other 3D geometry, and use that as a simple representation of the bolt without actually needing to model it. And like we said a moment ago, there is a way of assigning a cap screws as well. Cap screw option in there enables you to define cap screws and lock the screw associative to the 3D geometry. And here you can see the type of wagon wheel that's being defined as a result of creating this geometry. You can see down the middle there'll be a beam element, and then there'll be rod elements breaking from that and attaching to various elements and nodes around the 3D geometry, the perimeter of the entity that you're selecting to define it in the context of. Okay, so that's connectors. What about contacts? Well, contacts can be defined in a number of ways, and Nastran In-CAD has automatic surface contact generation. So when you define an analysis type, you'll see down in the bottom right-hand corner of the dialog box that you have contact data area, and this contact data area enables you to define the contact type, the default contact type, and the tolerance that would be associated to it. So this is the limit of gap that would allow for, or that would be an allowance for, when defining faces and geometry that is contacting and against those that aren't contacting. Further to this though, there's also automatic contact generation, and this is new for the 2016 release. It uses the CAD geometry to define contact pairs with inside assemblies or multi-body components. And it's an inventor-only feature. So if you're a SolidWorks user using Nastran In-CAD as part of your workflow, then unfortunately you don't have this feature available to you. If we look at contact pair generation, we can define this, like we said, automatically, but then there's also a manual process that can be either automatic or manual. So we can go in here and redefine specific parameters associated with the automatic detection of contact pairs. It allows for you to be automatically detected and generated using the solver, so there's no need to manually go through and process this. And the tolerance defines the maximum activation distance for auto, and so this is the area that's in the dialog box towards the top right. This is by default there's a direct relationship to a model reference dimension, which is typically one of the largest dimension of an individual component within inside your assembly, to give you an understanding of that tolerance and define the activation distance. Further to this, if we look at, and we'll be working through an example of this, of the ability to be able to use offset bonded contacts where you can actually define geometry manually. In this case, we've chosen a surface to edge definition type, but you could choose surface to surface, and you can define the various different types of interactions that various different parts of your assemblies and multi-body parts will interact, and how they'll interact inside the simulation environment. Beyond that, let's then step into some examples and have a look at how we can work with some parts. Now let me just make sure that everyone can see what's going on. Yep. Okay, so let's define, so what I've got here is a walkway or walk bridge, and what we want to do is we want to use some cables to define and locate this. So I'm going to start from scratch. This is the only thing that's been defined is some geometry associated with the way that I want to set up the model. Otherwise, if we go inside our environments area, we've got our Autodesk Nastran In-CAD. And by switching that on, we then switch into the Nastran In-CAD environment. The good thing here is that we don't need very complex geometry to be able to analyze and understand the interaction of this walkway. And the way that we're going to define it is we've got a plank essentially, and we're going to define it as a thick solid structure with two cables, and we'll have a pinned or hinged support at this end, so it'll be cantilevered at the other end, and we'll place a weight at the other end along with self-load to understand how this walkway is actually going to react to our loading. So in this case, let's walk through creating some materials. So I'm going to go new, and I'll just drag the dialog box across. Let's define the material that we're going to use. And the material is going to be from our library. So you can see there's hundreds of materials that are available. I'm just going to use steel mild and go OK. And we've now defined material as part of our library of materials that we can use inside of our simulation studies within Nastran In-CAD. Further to this, then we can define some physical properties. So I need to do this in this case for a couple of reasons. One, I want to associate the material to the walkway itself, but also want to change the type of element that's being used. So this is where you define the element type. So by default, we've got a number of element types, so solid, shell, and line elements. More typically, everyone associates finite element analysis with 3D element types, and we can see those just by accepting the defaults, hitting update, and then looking at our mesh, and you can see it's meshed the plate that we have, which is around, I can't remember how thick actually. Let's measure how thick it is. So it's 50 mil thick. It's defined the mesh in the context of this part as a solid mesh and meshes right through the part. We can, however, change that to be a shell mesh, and I just edit the physical property that's been created and change the element type to a shell element. We can then go and define the face that we want to use as a reference for the definition of the shell element. So I've split the part into multiple bodies. I'm going to choose the two faces that I want to represent as shells, assign a thickness to them, and go OK. The interesting thing is that if we just then update the mesh, you'll see that though the face is meshed using a quad element instead of a tetrahedral element, it has no thickness visually. The representation that we're showing, though there is 3D geometry there, the element actually has no thickness and is mathematically defined in the context of the analysis that will be run in the background. So we can't actually see the material thickness on our screen. Further to this though, we want to add a couple other things. So the first thing I'm going to do is constrain the part. So like we said before, we're going to define a pinned or hinged connection at the end there. I want it to be able to rotate around Z. So I'm just going to turn off the rotation constraint and then make sure that everything else is on. So it stops it translating in any of the X, Y, and Z, and it'll stop it from rotating around X and Y, and go OK. What else do we need to do? Okay, this is where we start talking about connectors. Now, a lot of what we've done can also be accessed across the top of the screen, but as you become more familiar with the environment, you might actually start using the model area, enabling you to define more advanced features and functionality inside the Nastran environment. Now, one example of this is connectors. So you can't actually access the connectors from the top of the screen along the menu bar, but you can access them down the bottom here. So I'm going to quickly just define a new connector. And you'll see this is the first time we've brought up the connector dialog box, and this is where we've got all of those connectors we were previously talking about. So rod, cable, spring, rigid body, and bolt. In this case, I'm just going to use the cable definition. I'm going to assign a parameter associated with both the area and the a moment of inertia. And apart from this, I'm then just going to define the endpoints of the cable. So from one end to the other. And I've got a line or a sketch that's been defined with inside that part just to give us a basis for using some geometry to define that. Click OK. So what you can see here is it's given us a visual representation of a cable. If we can edit it, go back in and just make sure that we did set it on cable. We did, yep. We've assigned the material here. We haven't assigned anything like slack or initial tension on the component, so we're just going to leave it the way that it is. And the other thing that we need to do here, though, is that we need to define the context of the point that we're referring to. Down the bottom here, the point is attached to the geometry, so it will bond that to our shell element. But at the top here, it's just a free point that's floating around in space. So we do need to define a new constraint here to restrain that point. Now I'm just going to use a fixed constraint, but you could use, say, a pinned constraint or give it some sort of rotational freedom if you want to, but I'm not concerned about that, and simply go OK. That will actually then mean that the part is pinned at the top here. We've got now a cable that's going to hang down attached to our plate and then give it some support. Now we want to do the same here, so in this case, instead of creating a brand new one, I'm just going to copy the existing one and paste it. Let's edit that one there. I'm going to clear the existing geometry, attach one point, the second point. You'll note that any properties that I've associated with it are then retained. But the one thing that you do need to realize is that when I'm copying and pasting features down in the model area, it doesn't automatically add them to the analysis type that's being run. So I do need to drag that up and add it to the analysis that we're conducting. Likewise, though, with the constraints, we've got that pinned constraint, not the pinned, the fixed constraint. I'm going to edit that fixed constraint and add the second point that we've got at the top of our part. Okay, so further to that, let's just add now some properties associated with the loads. This really is the only thing that's got to be completed. Is let's add a new load. And we want to define someone standing at the end of this walkway where it's overhanging. So I'm going to choose that front edge there, and let's define the load. So it's Y direction, and we'll assume that they're 100 kilos heavy. So we'll do 1,000 newtons and go OK. And one more that we'll add is a gravitational load. So we can add a gravitational load under here. We've got gravity, and the magnitude is going to be in the Y direction, minus 98.0. It's millimeters per second squared, so that's where we've entered that. Otherwise, we just go OK. So, okay, what's that look like? Let's run this and get a bit of an idea of what's going to happen. And it shouldn't take too long for it to run and solve this study. It's a reasonably simple analysis. We've got our results in a few seconds. So let's have a look at some of the information that we've gathered quite quickly. So we can look at our stress results here. So we can look at peak stresses in the areas. We're getting a peak stress around the connection point where the cable attaches to the plate of around 22 megapascals. We can look at displacement as well, so we'll display that. And we can see that the end of the part is displacing about 4 millimeters. So it's not moving very much, it's actually quite small. Okay, so I wanted to show to you that you can use these cable connectors in a different way. So rather than drawing lines, I do have some points here. And this is another thing to consider when you're using cables, because they do have quite a reasonable degree of freedom and flexibility to them. And so let's create a copy of this study and paste a secondary study in there. I'm not going to worry about renaming it. I could copy it. Obviously, it's good practice to name your analysis types relative to the things that you're trying to understand. So I would suggest you doing that as you're doing it. But just due to time constraints today, I'm going to push through. So the one thing that I'm going to do is I'm going to take away this pinned or this rotational constraint at the end of our plate and add some additional cables to hang down there and look at this in a slightly different format and the way that it's going to work. So let's remove the initial constraint, which is this one here. Remove it. Now notice that, as we've shown in previous webinars, removing constraints and loads and the likes that we're using with inside our analysis doesn't actually remove it from our model environment, so we can actually grab that constraint and reuse it again if we wanted to for a different study or for this study even. It's just removing it temporarily from the local study that we're working on. Let's add now some other connectors. So I'm going to, as we saw before, copy and paste 2 additional ones in there. Let's edit this one. We'll retain all the same parameters apart from just changing the points at which we're going to be running our cables. So we'll run one from there. Let's edit this one as well. And it's going to go from here to here. Go OK. And then, like we did before, let's just quickly edit the fixed constraint and add these 2 points on there as well, because they both need to be fixed as well. And go OK. So, as we showed, the reason why we can't see the blue lines showing up is that our connectors haven't been added to our study. So if we just drag those up there, we're then attaching those to the study and ensuring that we're actually going to be running them inclusive of that. Now the other thing that I'm going to do here is I'm going to change the study type, and this is one of the great things about the Nastran In-CAD product, is the ability to be able to quickly and easily transition between study types. So this is a linear static study, so it's going to run one analysis, whereas in this case what I'd prefer it to do is to run multiple analysis using a non-linear static. So effectively what it's going to do is it's going to apply the load gradually to our design and a number of times, and as a result of that it will then get a gradual increase, making sure that we're much more accurate results and taking into account the displacement and deformation of the part here. I expect that this will actually have quite high displacement, and that's the reason why I'm using the non-linear, is to make sure that on large displacement componentry here, like we have here, that we're getting reasonably accurate results. So I've changed the study type quite quickly. I've updated the study. I'm now just going to make sure that our mesh is up to date and hit run. Now you will see that this will take quite a bit longer than our previous study to run, because it's effectively running multiple times over the same study that was run previously, adjusting K-factors and remeshing and reanalyzing our structure, taking into account the displacement and deformation that the part is undertaking as the loads are being gradually applied. But you can see here that quite quickly, we're talking less than a minute, we've got a result back from our analysis, and let's have a look at some of our results. So in the first case, let's just turn on our results and look at them, and you'll see here that stresses, we've got our max stresses around 24 megapascals, and what else do we want? Let's have a look at our displacements. Now this is the interesting thing, is if we look at displacement, you'll find that we're getting very large displacement. So what's happening is that the part is actually shifting or twisting around the pivot point of these front two, and because this is a cable, it's got slack in it, it'll enable the rear of the walkway to rotate up and the front of our walkway to rotate down. So that's the reason why in this case we've chosen to use the non-linear analysis to make sure that we've got some sort of reasonable result from this study. The other thing that we'll look at is our cable stress, and you'll note that if we turn on cable stress, and we could have done this in the previous plot, we can look and see and understand. We'll just probe the cable stress results there. We've got about 63 megapascals stress in our cable. But if we hover over our rear cable, it's effectively 0. It's, you know, minus 9.2 to the minus 6, so it's a very, very small number, effectively 0. So the reason being is, remember when we said before, using cable works with tension or tensile loads, but it doesn't work with compressive loads. In this case, we are the cables would be under compression, and that's the reason why we are getting these compressive loads and effectively no stress. So there's one thing to keep in mind, and it's the reason why I changed those rear to the rear of the part to be, rather than be a pinned restraint, to have a cable, so that we can actually see in this case that the cables, though they work in one instance where we're under tension, under compression, you need to look at understanding your structure. If that's a concern to you, understanding your structure in a different way. But in this case, effectively the cable, it's under no compressive load and is just, under no tensile load and is in compressive load, then there should be very little issue associated with that anyway. Okay, let's now look at some other examples. So let's have a look at a welded plate. So we've talked about connectors, how to define a connector. Now let's talk about how we can define some contacts. And I'm going to switch into the Nastran In-CAD environment. This is a plate, it's the same plate. We've just located them in an assembly relative to one another with about a 5mm gap. And this could be like a weld gap or weld allowance for plates, but you still want to be able to analyze this structure. So how can we analyze this structure? Well, it's actually quite simple, and we'll step through the analysis of the part. So again, setting up from scratch, let's define our new material, and I'm going to choose the same materials we chose last time, which is just a steel, where are we? Mild, and go OK. And let's assign some physical properties. Now I'm going to assign 2 physical properties here. In this case, you could, if you would just go OK, effectively what would happen is you would be meshing the geometry completely as solid elements. But rather than do that, I want to define one part as a solid element and one as a shell element. So how can I do that? So if I edit that original physical property that I've defined and associate some geometry to it and choose the part or body, then when I mesh that, it will just mesh that body. It won't mesh the other body. Let's have a quick look at that. And you can see here that we've just meshed one body in the context of our assembly. If we were to run this assembly now, it would just disregard that this body was actually part of the simulation. So this body here wouldn't be taken into account. We can add another physical property. In this case, I'm going to change it to a shell element. And I'm going to choose the face that's going to define the element, make sure that I've got associated geometry turned on. And then it'll use that face with our assigned thickness. In this case, we'll assign a thickness of 10mm and go OK. If we now run our mesh again, you can see that it's meshed the face of our part, and the thickness is defined in the context of the shell and will be calculated as part of the analysis, not actually defined as a physical property shown here in the simulation setup. Okay, so let's add some constraint or a constraint. Let's define a fixed constraint to the end of our plate here, and let's apply a load to the top edge of our part here. Let's define it in the Z direction. It's going to be 100 kilograms or approximately that, and go OK. And let's run, and just we'll update our mesh just to make sure everything's good, and hit run and see what happens. Okay, Nastran solution failed. Now the reason why that's failed is because our bodies aren't touching. If they had been touching, based on our setup of our study, you'll notice in here that we've got our contact type set by default to bonded with a tolerance of 0.1. So any components within a tolerance of this range will automatically have a bonded contact associated with them. But currently this is, you know, too broad to capture the contact that we have here, which is 5 millimeters. So how can we resolve that? Well, there's a couple of ways. We could use automatic contacts, and automatic contacts would look through the model and look at all of the faces that we're touching or close to touching and predefine certain types of contacts for them, in which case then we would be able to go back and confirm that they were set up correctly and modify any of those that weren't. We can, however, also use a manual contact. So, and this is what I'm going to use here, is just a quick manual contact. And the manual contact enables us to define the manual contact in two forms, either as automatic surface contact generation or as manual. In essence, what you're saying here is we can define the contact type, in which case we want to be bonded, so we want to ensure that those two parts are moving in relation to one another. And we could just go OK, and based on the parameters that we've input into the box here, so the tolerance, the stiffness factor and all those sorts of things, we would detect any bodies and parts that were meeting those criteria and automatically assign a bonded contact to them. The good thing is that you can set up multiple criteria for multiple different surface contacts that would enable you to you know, quickly filter through your a multi-body part or assembly and define contacts. In this case, though, I'm going to use a manual contact. So this is the this is grassroots level contact definition, and we'll use an edge to surface type contact. So in this case, I can say, well, I want the contact to be between this surface and that edge. And I'm going to turn off maximum activation distance and have it automatically detect the appropriate level in this case. Like I said, I'm going to make sure that the bonded contact is selected in this case and hit OK. And then hopefully what we'll see is that now there's effectively a joint that's been created between those two parts. So the stiffness associated with this is actually defined with in context to the part material that's been used. So it's not an infinitely stiff connection. You will find that there is some flexibility in that joint. Let's update our mesh just to make sure we've got everything good. Hit run. And let's see what happens as a result of this setup and make sure that we've set it up correctly. There aren't any errors. Like we've seen previously, runs fairly quickly to give us a result. Let's have a look at our stress through our part. So you can see here that we've got stresses being shown. Now it's important to note that the stresses that are being shown there are the shell stress. So the shell stress is shown independent from the solid stress. So the reason why you could actually see high stress on the shell feature, but you know what looks to be low stresses on the solid feature is because it's been broken out to be shown as the shell stress. If you want to have a look at the solid stress, then come down here and go to solid von Mises stress, which would be the equivalent. And you'll find that we've now got stresses, and we can see those stresses through that plate and understand the stresses in the plate. So it's a limitation of working with a mixed mesh environment, is having to break down and look at the different element types in their different forms individually. The other thing I will talk about though is the deformation or the displacement of the part. So if we turn on displacement, you will see here that we are actually getting a nice transition through the part. So it looks as though that bonded contact has worked the way that we wanted it to. And to confirm that, we can animate our part and then look at the way that it's moving as a result of the load being applied. And you can see here it's reasonably typical of what we would expect under those type of circumstances. Okay, so that's a little bit about contacts. Now we will be running further information associated with contacts in a subsequent webinar, so please keep your eye out for that webinar. But otherwise I'm going to move on to finishing up with talking a little bit about using, and I'm going to close this one down, bolted connections and plates. In this case we've got two adjoining plates. So what we want to do is analyze this these two plates here in relation to one another and look at the bolted connection and the role that it plays in the way that we can set up our analysis studies. So Again, we'll shift into the Nastran In-CAD environment, and we've got our simulation set up here. I'm actually going to start from scratch. Let me delete out all this stuff. So rather than have it all set up for us, I might leave the material in there. I like the workflow of starting from scratch. So we'll leave the material in there, we'll delete that contact, and we'll just make sure that this has all been refreshed, which it has. Okay, so we've assigned a material. There's really nothing fancy about this. We've just said that this is a mild steel plate. Mild steel will be used in the studies here. Let's associate it to the geometry. Like we discussed before, as long as I've got add to FE model, it's going to be attached up here. And as long as I don't click associated geometry, then it's going to associate this type of material with this type of element to all of the geometry, in which case we're just going to go OK. To confirm that, just go update all, and that will actually show the mesh that's being used in our part to give us an understanding of what's being used in this case. Okay, let's apply a constraint. We'll, similar to the last example, we'll fix the end face of our part here, and then we'll place a tensile load at the other end. So we'll place a load, it's a force at the end. It's going to be in the Z direction, and we'll put a minus 1,000 newtons, so roughly about 100 kilos, and go OK. And we've now got our part ready to go. Now you could potentially try and bond these surfaces together and see how that goes, and you could maybe bond the hole centers together and see how that goes, but it's not going to be very representative of the type of connection that would be used. And there is a better way of doing it. And that, in this case, what we've got is we've got these connectors, and as we showed before, there's a couple of different bolted connection type joints that we can use. So in this case, I'm just going to choose bolt from the top, and I can choose two reference edges in this case that are going to define the context of the bolt. So you can see here that there's a bolt head on one side and a nut on the other side. We can define the bolt diameter. So the diameter that's been selected for us is based on the hole size. So I'm going to say it's a 12 mil hole. And we could go and define a washer thickness as well. So the washer height, which is effectively the thickness. So we can say, well, it's 1.2 mil on either side. And you'll notice now that there's a red representation of our washer. The materials that we're using in this case are defined here, but we can use it, add some user-defined materials. So if we wanted to, we could change those materials. It would make it easier just to set those up as a material that you would assign to all of the bolted connections. Likewise, there's a preload area where you can go in and associate a preload as a function of actual load or torque. Torque requires that you have the preload force as well as coefficient of friction. So we're not going to worry about that today. I'm just going to simply go OK. And then if we're to run this, let's have a look and see what happens. So it shouldn't take very long. It's a reasonably simple setup here. And our solution is complete. So let's have a look at displacement and get an understanding of what's going on. So you can see here, is that representative of what we would expect our parts to do? It sort of looks right, but the problem that I see is that the part is lifting up at one end, which is what we would expect, but at the other end it's actually interfering with the part. So quite clearly we can see that contacts haven't been either defined or defined in the right context to one another. So what we can do is we can quite quickly and easily define our contacts, and like we said, we could define automatic contacts in this case, but I'm just going to walk through the manual contact setup again and define contacts in relation to one another. Again, you could just go separation. You could leave it at auto and just go OK. And theoretically, that should actually fix this issue. So let's update all, just make sure that it's all good. Hit run and see what happens. So hopefully we'll find that we get a slightly different result than what we saw before, now that we've defined or better defined the types of contacts that we want to use. It shouldn't take a few seconds, more than a few seconds for it to run. Okay, let's have a look at that displacement plot again. Let's rotate around so we're looking at it from the right, and that looks a little bit better. So we're pulling away at the trailing edge, and then at the leading edge we're actually pushing down on the between the two components, and we're seeing more deflection of that lower component as a result of the upper component being pulled down. So that looks to be about right now. So you can see here that the idea associated with the creation of these bolted connections is the ability to be able to quickly and easily implement a connection type without needing or requiring us to model the 3D geometry. The downside associated with that, and let's just have a quick look at our von Mises stress for our part, is that we do get quite peak stresses around the edge of the bolted connection. If you're concerned about stress in this local area, so if you run analysis and you're finding that you're getting stresses very high and you should, or very concerning around a bolted connection, and you think that they're real stresses, then you really need to look at modeling or analyzing the structure in a different form other than using a bolted connection. A bolted connection is a good representation that quickly and easily enables you to implement that form of connection into the simulation environment, and gives very good flow-on effects as a result of doing that. The problem with using the bolted connection is that the very local results can be inaccurate, and the reason being is that we're making a number of assumptions here around how this actually is being restrained and held in position. There's effectively a beam element, and you can see it right up through the center of our part there, and from that beam element there's actually rod elements that extend out like a wagon wheel to the elements and nodes of the surrounding edge that we've chosen. In real life, the washer would extend beyond the perimeter of the edge of the hole and would be placing a tensile force down on the face, as well as potentially a torsional load as a result of the torque load that's applied to the part, which is a very complex joint to try and understand. So recognize that if you are getting very, very high loads that you are concerned about in these areas, then looking at those loads and stresses in that area needs to be done in a different format, potentially using actual 3D geometry to understand what's going on. Beyond that though, you can see that we can look at things like stresses. We can look at beam and bar stresses throughout our part. So let me just have a look at the von Mises stress of the beam. So you can see here our maximum stress on the beam, which is through the bolt, is about 3.5 MPa. So very little, and partly because a lot of that is only in shear loading, and the other reason is there's very little tensile loading. We didn't put a preload on the part, so yeah, so that's the reason why we're getting such low stress results through that area. Okay, so further to that, what happens if we wanted to use a different type of connection? Well, let's copy this result and paste it. So we've now got our second study here, and rather than having a through bolt connection, what happens if we had a cap screw type connection? Well, we can quickly and easily do that. So I'm just going to remove that connector, and let's define another connector down the bottom here, new. Let's add a cap screw. Again, we'll choose the top edge as the defining point of the head of our bolt, and then we'll choose this surface down the bottom here as the area where the cap screw will actually be retained. The head washer height, we'll put in a height there. We'll maybe make this one 2 millimeters, and the useful length, we'll put 35 millimeters. Again, we can define the material, preload and the likes, but otherwise hit OK. And theoretically, if we update all and they rerun our mesh, rerun our simulation, it'll take into account the different connector type in this case. So it's very quick and easy for us to switch out and look at the consequences of the use of different connectors in this case to represent our geometry. And we'll look at one final example of that in a moment to better understand what's going on. It's completed the results, and like we saw before, if I edit that, I can then display our displacement plot and have a look at what's going on and see that the part is acting in very similar fashion to the way that we would have seen, and hopefully you would find very similar stress and strain results as a result of that. Okay, so what's another way of representing this type of joint? Well, the way that we can do it is in a slightly different manner, and that is to represent it in a very primitive form. So I'm going to create another copy of the analysis, and rather than use a connector at all, I'm just going to delete or remove that connector. Let's look at it using beam or rod elements and then rigid elements to represent the connector, because in essence that's really what's happening. So this is looking at a very primitive way of representing this. There's no reason you couldn't represent these types of connections in this form if you wanted to. So the first step that I do is I create a new physical property, and the physical property is actually a line element that we're going to represent as you could use a beam or a bar. Bar is not going to take into account any bending, whereas a beam will. But I'm just going to assume it's a bar. We could assume a cross section. We'll put in here that the radius, and go OK, associate it to some geometry, and I've drawn a line that just represents the length of the bolted connection of our part. We can associate any preload to our part as well if there was any preload, otherwise just go OK. Beyond that, then we need to create a connector, and I'm going to create a new connector, and the connector type is a rigid body. So the rigid body is going to run from the vertex, so the end point of that rod that we've created, back to the edge of the bolted connection. And you can, if I turn on the display, I'll turn up the number of links, and you can see there's the wagon wheel effect of the rigid connections running back through to our geometry. I'm going to click on the new icon down the bottom there, and then I'm going to choose rod, which I've got. I'm going to choose the endpoint. Oops, sorry, not a rod, I want a rigid connector. Let's try that again. New, rigid, from that endpoint back to the dependence, which is that one there. Turn those up a bit if we want to. And this is where we can change from being a rigid to an interpolation, which doesn't have the rigid connection. Otherwise, we've now defined our part. Now, in essence, that should be enough to run the simulation, but what I've found as a result of doing that you actually need to change the contact type. So the surface contact that we've got here, and the other thing we've got to do is grab these connectors and add them to, oh no, they've been added, yep, and physical property, just making sure that everything's been added to our study. But our surface contact needs to be changed as well. So rather than being automatically defined, in this case, I'm going to manually define and choose a surface to surface contact. We'll turn on auto detect. I'm going to leave everything else as default, including the type of contact, so it's separation, enabling it to pull away from one another. And that should be enough for it to calculate and run this this mesh study. Hit run and give it a few seconds, and hopefully we'll get a result back, which will show us that it'll be reasonably similar to the previous results that we've run. In essence, this is very much the same as what the bolted connection type is doing, but like I said, we're doing it in a more of a manual grassroots type manner. and it's just finishing up now. So let's have a look and turn on our displacement plot display. And you'll see here, like we've seen before, very similar result. We're getting nice bending, very similar magnitude, and theoretically we should get very similar stress and strain results as a result of using that. So you can see here there's another way of representing a bolted connection, and potentially a way for you to represent a number of different types of connections using that method. Okay, so just moving back into our presentation, let's just finish off. So further reading, if you've got any further or you're wanting to gather some further information about the Nastran In-CAD product, you'll find a whole bunch of it available. The forums, the Autodesk forums are comprehensive. You can go on there and ask questions and answer questions and find out information related to all kinds of things that are going on, including if you're a user of Nastran In-CAD, contribute towards the design and development of the product. The Twitter account of the simulation team is at ADSK Simulation, where the team keeps everyone updated on everything that's happening inside the simulation field inside of Autodesk. Likewise, if you're on Facebook, Autodesk Simulation is the group there, so make sure you've joined up. And YouTube, Autodesk Sim 360 is the channel where you can find videos related to content like this associated with a whole range of simulation products. Locally, we've got a Future of Making Things group on LinkedIn, so if you're on LinkedIn, please make sure that you join the Future of Making Things group, where we're posting all kinds of information relevant to local manufacturing to Australia and New Zealand. And if you've got any questions, don't hesitate in contacting me directly. My details are up on the screen there. Feel free to shoot me an email or give me a call directly. More than happy to support any inquiries you have related to the product. Otherwise, we would normally take questions. People are a little bit quiet today, which is hopefully a good thing. If you do have any questions, feel free to come back to me afterwards. Otherwise, I'll thank you for your time, because we have basically bang on an hour. Thank you for your time, and hopefully we'll see you again next week. Thank you.